Hi students, I welcome you to this lecture video. I am Mahin Sultana, Assistant Professor in the Department of Electronics and Communication Engineering in R.M.K. College of Engineering and Technology. The name of the subject is Digital Electronics. So in this Unit 1 Minimization Techniques and Logic Gates, we are going to see what is 1's and 2's complements, why it is used and different types of codes. So what is complement? Complements are used in digital computers for simplifying the subtraction operation and for logical manipulation. Okay, for whatever the manipulations or subtractions we are doing, we are using these 1's and 2's complements to simplify the process. So, let's see what is 1's complement. 1's complement 1's complement. The 1's complement of a binary number is defined as the value obtained by inverting all bits in the binary representation of a number. Basically, what's 1's complement is? The 1's complement form of any number is obtained by changing each 0 in the number to 1 and each 1 in the number to 0. So, whatever the binary number is given, where all 1 is present, we will be putting 0. Where all 0 is present, we will be putting 1. This is what is called 1's complement. So it behaves like a negative of original number. So if you are able to understand, let's move on to the 2's complement. 2's complement is nothing but we studied what is 1's complement type. So when a binary number is given, where all 1 is given, it is replaced with zeros. Where all 0 is given, it is replaced with 1's. So the negative of the original number. To that, if you add 1, it is the 2's complement. Okay. So you can understand it easily with the help of examples. So first one, if you see, find 1's complement for the given binary number. This is the given binary number. How will you find it out? How can you do it easily? So see, finding 1's complement is nothing but inverting. So whenever you are getting 1, you are adding 0 there. Wherever you are getting 0, you are adding 1. So if you are able to see, the 1 gets converted to 0, 0 gets converted to 1 wherever the corresponding value is present. So if you see the second problem, 2's complement for the same binary number they have given. Okay, so same binary number is present. So we have to do 1's complement first. What is 1's complement? Adding zeros wherever 1 is present and adding 1's wherever 0 is present. So you are writing it. So you are adding it with 1. So if you add it with 1, you will get a value, right? That is 2's complement. Okay. So you will be using this to simplify the operations. So 1's complement subtraction. They have given a question here. 1's complement subtraction for 10 minus 14. Both are decimal numbers. So if you are able to see, you are writing binary equivalent of 10 here. Binary equivalent of 14 here. Okay. So this is 1's complement. So only doing 1's complement is enough. For what you will do? For 14 you will do. Second value is 14. For that you will do. Okay. Second value is 14. Okay. For that we will do the 1's complement. 1's complement is nothing but where all 1 is present you will put 0. Where all 0 is present 1 you will put. So 111 gets converted to 0001. Okay. So you are getting the value. Now you have to add. See you will be thinking like they have given subtraction and why are we doing addition here. See students, we have done inversion here. 1's complement is nothing but getting a negative of the given number. So since already a negative number we have taken, we are doing addition here. Okay. So 0001, when you add it with 1010, you will get 1011. Since there is no carry, this is a no carry condition. Since there is no carry here, okay, what you will do? You will do 1's complement for the output obtained and you will put a negative sign in the front. If there is a carry, you will write whatever value that's obtained. Since there is no carry, listen carefully, since there is no carry, you will do the 1's complement for the output and put a negative sign. That is very important. Negative sign in the front. 2's complement subtraction. Perform 2's complement subtraction. 10 to the power of 10 minus 14 to 14. I mean 10 to the prefix. That is, this is a decimal number. When 10 is present, is a decimal number. 10 is a decimal number. 14 is a decimal number. You have to perform a subtraction for this using 2's complement. So you are writing a binary equivalent for 10, binary equivalent for 14. As I already told you, 14 is the second value. So for that you will be taking 2's complement. You have taken 1's complement first. Triple 1 0 gets converted to triple 0 1. Ones and zeros are replaced. Now adding it with 1. If you add it with 1, double 0 1 0. Since 1 plus 1 is 1 0, 1 goes to carry. So 1 0 comes, 0 0 will come down answer because there is no value. So this is the 2's complement of 14. Since here also we are doing an inversion, 2's complement we are taking, we will do addition here. So 14 plus 10 you are doing. 1 0 1 0. You are getting a value. Double 1 double 0. Okay. So since you are getting this value, you will perform 2's complement for this value. When you perform 2's complement for this, you will get a value 0 1 0 0 and prefix it with minus, because this is again a no carry condition. There is no carry. So you will do 2's complement to the output and you will get the value. For that you will prefix minus. So this is the desired output. Perform 2's complement subtraction. 14 minus 10. That was 10 minus 14. This is 14 minus 10. Both are decimal numbers. So you will be taking binary equivalent of 10 first. Then binary equivalent of 14. So you are taking binary equivalent of both the values and you will do 2's complement for which value? 10 you will do. 2's complement for 10 is 0 1 0 1. Okay, when you are taking 0 1 0 1 here, I mean, yeah, you are adding 1 again. 1's complement is 0 1 0 1 you are doing, you are adding 1 again, you are getting a value here. So that is a 2's complement of 10. With that you are adding 14. Why you are adding is, I already told you, we have done a complement here. So you are adding already. So when you are adding, you will get a value 0 1 0 0 and 1 here is the carry. The desired value is 0 1 0 0. Since you are getting a carry, you will write the answer directly as 0 1 0 0. This is a carry condition. So you'll write whatever you get as the answer. So another example, if you see 2's complement subtraction. 42 decimal minus 68. This is a decimal value both. So 42. 42 you are taking and writing here. 68. See, this is a weighted. You are writing the binary values by weighted method. You are writing the above values as 1, 2, 8, 4, 8, 16, 32, 64. These are the weights. So wherever you are taking it as 1, you have to add those values to get the corresponding decimal value for the binary value. See, 4 you are adding with 64, 68. So this is the decimal value for 68. 42. See, 32 with 8 plus 2. 40 plus 2, 42. You are getting this easily, Noma. This is how you will get. You will you'll weigh the values and add it and then you will get the value. Okay. So you are performing 2's complement for 68 since 68 is the second number. So 68 you are doing 1's complement first. You are inverting the values. See, if you are able to see, the values are inverted. 1's complement is performed here. Then you will add 1 here. When you are adding 1 here, 1 plus 1 0. Again 1 will go to the carry. 1 plus 1 0. Again 1 will go to the carry. 0 plus 1 is 1. Whatever value is present, it will be written as such. So here we are doing addition because your complement is already done here. So we are doing addition. 42 is being added. 0 plus 0, 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 0. 1. Again 1 plus 1 is 0. 1 goes to carry. 1 plus 1 is 0. Again 1 is there. So 1 you will write here and again 1 will go here. 1 plus 0 plus 0. Again 1 will come. So you are getting the value. This you don't have carry. So this is a no carry condition. So what you should do? You should perform you should perform 2's complement to the output and add minus in the front. So already if you see 1's complement is performed here. 1's complement, 0 is converted to 1, 1 is converted to 2. I mean 1 is converted to 0. So if you add both, if you add it with 1, you'll get a value, right? That is the desired output. Okay, since it is a no carry condition, you have to take 2's complement for the output. So what is the next topic, ma? The next topic is codes. What are codes? What is coding generally? Why is coding being used? Coding is nothing but the process of assigning a group of binary digits to represent multi-valued items or information. Say for example, I am having a lot of data or information that I am storing it in the form of codes. For that I need some codes. Okay. For that only this coding is used. There are two types of codes, okay, weighted and unweighted. See, if you see binary code, digital data, as I already told you, represented, stored and transmitted in the form of bits. Okay, this group of bits is also called as binary codes. The bits we are using are binary codes. Okay, so there are of two types, weighted codes and unweighted codes. What are weighted codes? In a weighted code, in the previous problem also we saw, right? We gave weight, that is 1 to the specific values of 2 to 1, 2, 4, 8, 16, 64. In that manner we gave, right? In that we gave a weight, and when we calculated the corresponding values, we got the decimal value, and where remaining places were filled with a 0, we got or binary value. See, in 8421, if you add 1 here and 0 here, see, if you are adding what are the values that are weighted, when 1 is added, that values are weighted. 4. 4 plus 2 is 6. So, this is the binary, corresponding binary number for 6. And when you add this 2 plus 4, 4 plus 2, you will get 6. Okay, 0, 1, 1, 0, you will get 6 as binary value, and this 6 you are getting. Weighted binary codes obey the positional weighing principles. That is what? Positional weighing principles. These are the positionals. These values are being used to calculate. That is the positional weighing principle. Each position of the number represents a specific weight. So this 1, 2, 4, 8, 16, 32, every value as it increases, this holds some weight. When 1 is added, that weight is gained. Okay, so when you add it, you will get a decimal value. When the remaining places are filled with a 0, you will get the binary value. Okay. So unweighted codes. Unweighted means non-weighted. Okay. These codes are the codes that are not positionally weighted. There is no positional weighing here. Okay. Whatever is present is already that is present. This means that each position within the binary number is not assigned a fixed value. Here there is a fixed value, right? Here there is no fixed value at all. So for example, gray code and XS3 code. What is the gray code? Gray code is nothing but it is a binary number system in which successive pair of numbers differ by only one bit. Only one bit difference is there. How a gray code is being calculated from a binary code is through XOR method. See, we'll use XOR gate and the XOR calculation is done. In the next slide, we'll see. See, for example, binary to gray code conversion. Convert 1011 binary to gray code. This is a binary code. 1011 is to a gray code. You are writing it as such. Okay. Remember one thing. Always first value of a binary code will be the same for the gray code. And second value, what you have to do is you have to XOR first value and the second value to get a second gray code digit. You have to XOR second and third binary digit to get a third gray code digit. You have to XOR third and the fourth values to get a fourth gray code digit. Okay. So 0101 binary to gray code. 0101. So as I already told you, first value you have to write it as such. Okay. How you will get the second digit of the gray code? You have to XOR first and the second digit. Then you will get the second digit of a gray code. Then XOR second and the third digit of the binary code. You will get a third digit of a gray code. XOR 0 and 1. You will get a what you will get? You will get fourth digit of a gray code. You will use in this only binary to calculate the gray. But in gray to binary, the method is somewhat different. You will use gray and the present binary value to get the next value. Okay, see, gray, whatever the first value is, it will come as such. So, it will be written as such. You will XOR this one and this one, and then you will get a second digit of the binary code. You will XOR first digit of the binary and the second digit of the gray. so that you will get the second digit of the binary. Same way XOR binary, present binary value with the given grade third digit, then you will get the third digit of the binary value. Then you have to XOR this third digit with the last digit of the gray code, so that you will get the last digit of the binary. So this is how the conversion takes place. Okay, ma. So what is XS3? XS3, as the name suggests itself, there is 3. Okay. The code doesn't have any weights because it is, we already studied, it's a non-weighted. Okay. Or unweighted code. See, XS3 code of a decimal number is obtained by adding 3 to the decimal equivalent of the decimal number. Okay. See, binary equivalent of the decimal number. See, binary equivalent is these values. To that, if you add 3, you will get a XS3 code. Okay. So this is, as you know, 0. This is, if you add 0 plus 3, you will get only 3 value. So you are writing 0, 1, 1 here. This is 1. 1 plus 3 is 4. So you are writing 4 equivalent value to this. 0, 0, 0, 1, 0. Okay. This is 2. So 2 plus 3, 5. So you are writing fifth value here. So it starts from 0, it starts from 3 only. So whatever the BCD value, binary value is present, if you add it with 3, the output resulting is the XS3 code. Simple as it is. Okay. Alphanumeric codes. Alphanumeric codes are nothing but, if you are able to see alpha, if you are able to split it like this, alpha plus numeric. Alphabet plus numeric codes. Alphabets are used, numeric values are used, mathematical symbols are used to represent the data whatever we are having. Okay, see, character codes used represent the alphanumeric data. This includes letters of alphabets, numbers, mathematical symbols and punctuation marks. These are nothing but, for example, you can take it as ASCII. See, it is a combination of alphabets, numbers, mathematical symbols and punctuation marks also. Okay, ma? So, thank you students. Thank you for listening patiently. With this, we'll wind up our lecture.